the second speaker this morning, Yuan-Pin Lee from Utah. The title of his talk is Functoriality in Gromov Witten theory.
I want to thank the organizers for the invitation to speak in this conference. Let me start by saying I do not have a proof of the conjecture by Kazakov conservation context. So if you're coming for this, I'm sorry, I don't have a proof. But I will talk about the general philosophy we have about the functoriality in Gromov Witten theory. So the main problem with Gromov Witten theory about functoriality is Gromov Witten theory does not have any manifest functoriality. So, for example, the quantum core march does not pull back or push forward, etc. So that's the main problem, and so therefore a lot of things we would like to have, we don't have, and so we have to find another way to address this issue. So what we really want to have is some sort of functoriality with respect to first regular embedding and the projection. And so that's because usually if you study any projective morphism, then you know that by definition of projective morphism, you can always factor that through so this guy, and so, oh, by the way, so everything I'm talking about today is going to be, the spaces are always smooth. It can be orbifold, but it has to be smooth, and I'm always over the ground field of complex numbers. So you can factor this through regular embedding, and then this is going to be projective Banto, so this is projection. So if you can work out functoriality with respect to regular embedding and projection, then you will have a very general functoriality. However, in this case, we cannot. So the best so far is the following. So first, you cannot do any general regular embedding, but you can, when this map, let's call it I, if I is hypersurface, or complete intersection, then you do have some kind of functoriality, and this functoriality usually called quantum Lefschetz. Because classically, Lefschetz told us if there is some kind of hypersurface, then there is a relation between the classical core march between the smooth projective variety and its hypersurface section. So there is a quantum Lefschetz. So that's. Yeah, but so I should say this. Yes.
Is it possible that the same morphism between x and y can be factorized in two ways?
Yeah, you can factor in many different ways.
In that sense, if the construction will use the factorization, will not It will depend on.
Yeah, exactly. So functoriality should not. So in a sense, functoriality should not depend on how you factorize this. And well, I mean, as you know, so this, if you can do it in general regular embedding, then this projective bundle can be any, can be very trivial projective bundle. For example, can be projective, just trivial projective bundle, projective spaces over one. But since you can, this regular embedding has to be constrained. It can only be have complete intersection. So you want to minimize. So in this process, there is some kind of loss of information. Just like in usual classical Lefschetz hyperplane theorem, so there is some kind of loss of information. So you want to minimize the loss of information. So you want to carefully choose this so that you will choose. And in that case, you want to prove a little bit more general functoriality with respect to projection. And so if this guy, let's call it pi. This pi is really a projective bundle over the base. So this will be some kind of or you can do this in more generally toric bundle. But projective bundle, I mean, not more generally, but you can also do it toric bundle. And so this projective bundle, you can be very choosy, and so this projective bundle, so this relation, this kind of functoriality is called quantum Leray-Hirsch. So let me. So now we have. Assume that we have this kind of a two new tools, and let's try to see what we can prove about the functoriality of this Gromov Witten theory. So maybe I should first say a few words about quantum Lefschetz. So quantum Lefschetz, there are actually two components of quantum Lefschetz. The first component is to relate. So if you have X embedded in Y, and you have an ample line bundle. Such that, and you have a section such that X is a zero section of your line bundle. And then the quantum Lefschetz usually, so it try to relate Gromov Witten theory. So you try to get Gromov Witten theory of Y, and then you want to get as much information as possible to Gromov Witten theory of X. And so this in genus 0, so quantum Lefschetz, this in genus 0, it's in a pretty good shape. In a very good form. And I guess starting with given the proof of mirror conjecture, etc. So you have a pretty good grasp in genus 0. In higher genus, and there's certain properties, it's not very good. So I mean, there is existence of some form, but still not very good. So in genus 0, the main strategy is the following. So you start with, you want to first relate the virtual cycle of, so you want to start with relating virtual cycle in genus 0 of X let me omit all the informations. You want to relate this to some sort of genus 0 information of y. And you start with this, with some kind of a induced bundle. And this form was first, I guess, proposed in Konsevich's original attempt in the quintet case. So you want to first relay this, so this will be geometric part of this. And then you try to unravel this part of information so that you can get information of Gromov theory of X to Gromov theory of Y. So that's we'll come back to this later. And so quantum Leray-Hirsch also is in pretty good form in genus 0. That's also in a very good form. So I will say more about that. So okay, so now I've talked about the two available tools. One is quantum Lefschetz. The second one is quantum Leray-Hirsch. So assuming we have these two tools, what can we do? And what are tools we have? So another tool we can have is basically Gromov theory is deformation invariant. But deformation itself will not tell us much. So you want to deform to something slightly singular. So that's the third tool we can have is degeneration. So the degeneration says that the Gromov, so if you start with your Gromov theory on X, and you can deform X so that the central fiber can be slightly singular, and this how singular can it be? This depends on what kind of degeneration formula we can get. And then I guess the double point degeneration like this, so maybe this is not a good picture. So let me do it again. Maybe I'll say this. Something like this. So this double point degeneration is, so in the Gromov theory of X, by some sort of a deformation invariance, this is the same as Gromov theory of X here. And by this, we still don't get much information. The Gromov theory of X0, the same as that doesn't tell us much. The important thing here is this guy can be written as some sort of Gromov theory of, let's call this X1, X2. Some sort of relative Gromov theory of X1. And this is one of a divisor. This is double point singularity, and so you have a divisor here. Somehow, the information comes from Gromov theory of X1, D, and X relative Gromov theory, X2, D. And so hopefully you can, in this kind of degeneration analysis, you can get Gromov theory of X from Gromov theory of X1 and Gromov theory of X2. And this is not usual Gromov theory, but relative Gromov theory. Still, the geometry of this can be simplified in some way, or in other ways, they can be more suitable for our analysis. And so in this kind of study, the fourth tool we have is the Novikov ring. And so that's, once you have Novikov variable, and this Novikov variable is this is new. This is only a variable in quantum case. There is no classical counterpart, and so if some Novikov variable with respect to certain numerical variable, the Gromov Witten theory proved to be analytic function, and this is then it's possible to do some sort of analytic continuation, and that will give us a better understanding of this functoriality. And so far, it's been very vague, my phrasing, but I just want to bring these four variable tools out so that we'll see how we can use them. And the first example I will give is this is maybe do the ordinary flux. And this is a special case of something called K equivalence, or Gromov transformation. Oh, what is this? So this will use three of the four tools I mentioned. So you start with your space X, and then X you have, and you want to so the X has the flopping contraction to X bar, and then you want to compare with Gromov Witten theory of X prime, which we call it a flop. And so what is the ordinary flop? Ordinary flop is, say, I have the exceptional, so these two are birational, and so their difference is some kind of surgery. And what kind of surgery do I have? So I have this, in this case, the X minus Z will be complete isomorphic to X prime minus Z prime. So that's the exceptional locus they have. And the exceptional locus will look like it's going to be over some kind of a projective bundle. So this is going to be the exceptional locus is projective bundle. And not only that, so this the normal bundle of this exceptional locus here is actually because now this Z is a projective bundle, so you have this. Let's call this phi bar. Sorry. So some. So and then the picture here is symmetric. So this guy is going to be the projective bundle over the same base. So these two are actually the same. And so the picture here is completely symmetric. So you have this prime, and then the normal bundle is going to be and so I assume the rank of F is the same as rank of F prime. And this, in this case, let's call it R plus 1. So this is the projective bundle over the space. If this notation already too complicated, so you think about the simplest case of this. The simplest case of this is the following. So if you take S to be a point and R to be 1, So that's the simplest case. So now what you have here is this Z is going to be, in this case, Z is going to be P1. And then the normal bundle of Z is going to be O minus 1. Because this is rank 2 bundle, So in this case, what you see here is, so this is a case, this is usually called a TF1. And so this is, so in this case, of course, dimension of X is 3. So in this case, what can we say about the Gromov theory? And so, and you also see that this is the PR. So this is a P1, and then the normal bundle is O minus 1 minus 1. So on the near the exceptional, so on the exceptional locus is Calabi-Yau alone. And you can see that's why they're K equivalent and or correspond. This is the correspond case. So how can you show? So we want to show that. And so what do we know about this functoriality? And we want to be able to say, so maybe the theorem. So the rough form is that. We want to show that the quantum cohomology or Gromov theory of X is equivalent to quantum cohomology of X prime. But how can we do that? So we start with classical. And we want to get this rough form to the best possible. So best possible form of functoriality. And so let's start with this case. So first of all, I want to, if I want to identify quantum cohomology, I better first identify classical cohomology. So you want to first identify classical cohomology, and you use identification to identify your quantum cohomology. And so what do I mean by this? So first, you want to show that there is a natural correspondence. And this natural correspondence is the following. So this is, you get from, and then there is some kind of cycle. And so let's say if you have your F here, and then this gamma F is your graph here, but you take closure. So it becomes some kind of gel class in the product. And this F is the correspondence between the cohomology of X and cohomology X prime induced from graph closure. And this is induced from graph closure. And you can prove that this is F is isomorphism. In fact, it's stronger. It actually identifies the child motif and in particular Functoriality. However, this correspondence does not identify the ring structure, and that's the main thing. So, So, and then you say, well, quantum cohomology, deformation of classical cohomology, if it doesn't preserve the classical cohomology ring, how can you preserve quantum cohomology ring? And that's where the analytic continuation will come into play. So it does not preserve ring structure, and in fact, so now what can I say about this? In the quantum case, now I fix this F. I want to use this correspondence to identify all the information between these two. And in particular, for nomical variable, I want to send nomical variable to this. So this.
Excuse me,
Yes.
This is not quantum cohomology, we speak about differential along the second cohomology quantum cohomology.
Well, let's restrict on the even part.
Even part.
Yeah. But most of this can be applied to our part as well. But for our purpose, let's restrict the second part. And if I insist on this, then there is also a problem because you can actually, even though it preserves this, but when you try to, and so remember, I've contracted one projective bundle or projective space over this. So this projective space has. This is a line class of the fiber class of my projective bundle. And so this is a fiber-wise line class. And if you take your fiber-wise line class map over, you'll be, but it also does not preserve, this is a non-effective class in X prime. So that's another problem. So this is of course then FQ of minus L prime is different than Q of minus L prime. It's not in the nomical variable of X prime. So because this is not effective. So the solution to all these is you have to do analytic continuation. First of all, you want to show that the solution of this is show that Gromov Witten theory of X is analytic with respect to the flapping curve. So this is particular nomical variable. So by this I mean nomical variable corresponding to the curve which perform the flapping contraction. In this case will be this sort of a result countable case. This will be P1. This P1. So we want to first show this analytic with respect to this. And so now you can say that as an analytic function, I'll say a little bit more about QL. So this Gromov Witten theory of X is the series expansion at QL equal to 0. And the Gromov Witten theory of X prime is series expansion at QL equal to infinity. Or in other words, it's QL or QL prime equal to 0. So that's what one can show is the Gromov Witten theory of this guy and that guy is they're actually the same Gromov Witten theories on P1, and then if you expand at 0, you get Gromov Witten theory of this, expand Gromov Witten theory of that. And so far, most of other cases proven were by computation. So this kind of per quantum transformation conjecture or things like that. And so, but you remember, I cannot compute anything because my X and X prime are very general. I only give some constraint of local structure. near my surgery. So what can I do? So a key step to perform this is to do degeneration. So you start with your x, and maybe you with some kind of z inside this. Now you do the sort of trivial degeneration. This is called deformation to normal cone. And then what you have here is, so if you do this classical deformation to normal cone, what you have here is the following. Something like this will happen. And this becomes x tilde, where this is actually brought up z x. And this guy is a projective bundle over z of the normal bundle of z inside x, but you compactify it. And so this is your, so they are glued along a divisor, shear divisor. And so, and this, as I said, this a priori doesn't help us because we don't know x, we don't know x tilde, but this guy is simple. But now if you do the same thing with x prime, and what you'll get here is you will get the same thing. So like here is x prime tilde. In this case, it's a brought up of z prime x prime. And then it also has this. So sorry, so maybe I should draw it slightly different to emphasize their difference. Draw like this. And so again, this part is your projective bundle. And this part is x prime bar. But if you look at the picture, if you draw it up again, then you actually see their x tilde is the same as x prime tilde. And this is just like this case. If you roll this up, then you will see they're actually the same upstairs. So what you get here is this. This roll up is actually the same. And so in order, so if there's any way, so these two become the same. So if there's any way I get information from these combined two to here, and then these two to there, then I will be able to get information. So I'll be reduced. So the degeneration formula reduce the comparison to these two. And these two, as you can see, these two are just some kind of a simple complication near the exceptional locus to what we call local models of ordinary flat. And so these two, now these two, what are these two? These two are actually some kind of a projective bundle over projective bundle, right? So remember, this guy, Z itself, is a projective bundle. And this local model is a projective bundle over projective bundle. So it's some kind of toric bundle over a smooth subvariety S. And so now, but S also, again, are the same, as I emphasized here. S are the same. So now you reduce to local models, which are somewhat the double projective bundle over smooth base. So now what you can do here is to say that, okay, so I only have to compute these two. But to compute these two, I start with the same S. And then I have different, so I'm reduced to local models, which are double projective bundle. So now the task is much easier, and then you can deal with double projective bundle over the same base by the quantum Leray-Hirsch. So that schematically is what one can do with this kind of. Then after, there's still some hard work to do, but schematically that's how one can deal with this case of flux. So this is the simplest case, and strange enough, this is so for quantum coherent, this seems to be the best functoriality because they are actually the same. It's just like their analytic configuration from one to the other. So the second example will be to deal with grow up along complete intersection centers. And you'll see why I need complete intersection centers, and that's because quantum Lefschetz, the problem of quantum Lefschetz. Okay, so let's see. So let's start with, again, X is smooth projective variety, and Z is smooth. Is a smooth center inside X, and I want to blow up along this. So let's follow this. And suppose I know Gromov Witten theory of X, I want to compute Gromov theory of X tilde. Well, so how can I do this? And you know that there I don't have to compute because I'm comparing these two. So as long as they're the same, I'm happy. But here I do want to compute X tilde, and so what can I do? And so far we haven't developed a good technique of this, and so let's try to see if we can use these tools that help us computing this. So assume that the Z is complete intersection, and then in fact, so you have line bundles. So that means it's cut out by sections of very ample line bundles. So Z is, and a priori you will see that X tilde has nothing to do with, Z is complete intersection, but that's not what we want to compute. We want to compute X tilde. And X tilde has nothing to do with quantum Lefschetz or quantum Leray-Hirsch. So that's where we will come into. So, and then it's easy manipulation that you will see the following. So in other words, you have this section which surjects this. You want to think about this surject ideal sheaf of Z. And so now from this diagram, it's easy to see that, so you have an embedding of this. So you grow up of X tilde. So X tilde grow up becomes a subscheme of this. And this is over X. And this usually is not complete intersection either. So, but what we know about this embedding is that there is a universal. So maybe what I will call this is. So let's give this a name. Vector bundle of this. So we have a vector bundle, and then you can pull back this vector bundle here. And there is a universal subbundle. So logical bundle, let's write it as O minus 1. And there's a universal quotient bundle. And then you have this sigmas, which give you a section. So of course this sigma induce this section here induce the section here, and which can be then project to this. Oh, that's not very clear. The section here, sigma, induce the section here. Let's call it sigma q. So in this case, what can we do about x tilde? So we're trying to compute the Gromov Witten theory of blow-up in two steps. First, we want to go to its projective bundle, but projective bundle is good because we have sort of quantum Leray-Hirsch. We can go x to its projective bundle. Now we want to go from projective bundle to its but this is so a simple lemma is that Z is complete intersection center. Then you get the zero section of this induced section is actually the same as x tilde. And so that's very close to complete intersection, except now this Q is in general non-split, and it's not direct sum of line bundles. It's not complete intersection in this case. Still, it has a good property, and so let's try to analyze its good property, because I mean from here you can see. However, we do know this. It's so we Q is something called convex vector bundle. In the sense that if you have a non-trivial, for any non-trivial map, for any non-trivial, then you pull back Q. So it has some kind of positivity, because it has inherent positivity from this L are all very very ample, so they're all positive, etc. So you can easily prove this. And so in the same way, I explained the quantum Lefschetz case. There is some kind of generalization. You can actually show that in this case, can be written as the virtual class has this comparison, so some kind of generalization of conservative formula. So this Q and Y is some kind of induced bundle to this by pull back to its inversal curve and push forward, and because of this, so you only have actually zero, and so that's bundle, and you can take the top chain class, some kind of abstraction, so similar to some kind of abstraction bundle. So this formula is still correct, and this in this general form, it's observed by Kim Kresh and Tony Tantet. So they observe, so sort of they observe that this is actually true from the general property of virtual classes. So now we're sort of we're relating this to so now we can compute this by knowing if we know this. But this guy again, remember now we want to go from Gromov Witten theory of X. Now we can go to Gromov Witten theory of projective bundle of X. So this is a quantum Leray-Hirsch. And now we do have this, but this one is not usual, not the usual quantum Lefschetz form. So so we want to use quantum Lefschetz. And so what can we do? You observe that there is such a form of this. Here is the universal short exact sequence. And so, and by some kind of a multiplicativity of this, you can say that this actually is the same as V. Now all these are split bundles, and then you can apply sort of a slightly generalized quantum Lefschetz. You'll get Gromov Witten theory. That's true. And so this, unfortunately, as I said, I don't have a proof of the general conjecture of Korsakoff consideration and Pantev, because this only works in the complete intersecting center. And if it's not complete intersecting center, you still have this kind of subjectivity, and it still embeds. But then, but this is not correct. In general, you will have when Z is not complete intersection, you will have much more contribution than this. This will be actually some kind of an X to the union of so all the fibers. And in this, in the complete intersection case, this fiber over Z happens to be just the Z tilde, the exceptional divisor. So it's sort of absorbed into this. But this fiber can be very, very large. And one can try to so to get more general broad formula speculation is the following. So is maybe you can start with, for example, you take Z to be a twisted cubic, and X to be P3, the simplest. Then you will try to study the blow-up of twisted cubic in P3. The simple example can think of where this Z is not complete intersection. And so in this case, maybe you can try to do the following. So you take a family of ideals. So that I0 is IZ. But then you can try to make this into a family such that this family of ideals over P3 cross A1 or P1 is this guy is the same as IZ. But then you just freely deform. So these twisted cubics are defined by three quadratic polynomial. So I don't know, it's called P1, P2, P3. Oh, maybe not so good for P, so F1, F2, F3. And you can do some kind of general deformation of this. And then this 3 quadratic polynomial in P3 will intersect only at, so general when, this will be F1T, F2T, this is T, sorry, so F3T. And so in this case, it may be, so this will be, so if you take your P3 cross A1 or P1, then you grow up along this ideal of this. Sorry. So what you'll see here is the family will become some kind of the family will be in the general fiber. You'll be the grow up of 8 points, and so there are 8 P2s involved, and grow up points usually are not so hard. One can probably deal with that. So the general fiber of this A1, my T variable will be the general fiber will be the grow up. So this will be grow up of 8 points in P3. The special fiber will be not just the grow up of P, not just X. There's one part which is X tilde, which is grow up of twisted cubic in P3. But then there is another part, because I mean, the grow up center is not flat at 0. So I mean, it doesn't commute with space change. So when you do that, it will be similar to what you have in the case where this will be some kind of projected bundle over Z. So maybe from this diagram, one can try to get this information. Knowing the grow up of 8 points and this projected bundle, which is not too bad because this is the P1, and so this is the bundle over some kind of toric, so projected bundle over P1. And so that's also probably okay, and it's probably okay, and hopefully one can get information on this. Just some kind of speculation. I haven't been able to finish that yet. So that's the second example. The third example is to do something in between these two. So now we have grow up, and we have we have grow up, and in some sense, in some cases, special cases, and we have the flap, and then there is something actually connect these two, namely what we call alternate flips. So it will not be Crepon in this case, not K equivalent. So in this case, it's very similar to what we had before. So you start with the X, and then you have an exceptional locus Z here. Now exceptional locus Z is also some kind of projected bundle over, so this is X. You have a flipping contraction to S bar, so that this Z over S is actually some kind of, again, projected bundle over this. And normal bundle is also except in this case, the rank of these two bundles are not symmetric. So the rank of F is R plus 1. and rank of R prime is R prime plus 1. And if this is going to be, if R is equal to R prime, then you have on the other side, you would have the flapping contraction, the flap I talked about. But now assume R is greater than R prime. Then what you have here is this is a PR bundle over base. And the other side will be PR prime bundle over base. So it will be smaller, your surgery out a bigger Fauré space in exchange of a smaller Fauré space. Again, the simple example will be, so you want to think of S as a point. So you surgery out PR and then surgery in PR prime, and so R prime is less than R. So if you compare now the cohomology, so you can do the same correspondence I talked about. So if you do the same correspondence, just use the graph closure because this is still birational. And you can do the graph closure I talked about, and then what you will see here is this one. This one has more cohomology classes than that. So you expect this guy to be surjective, but not injective. And so there is some kind of kernel. And the dimension of this will be exactly the number of classes you lose in this surgery. In fact, this is like the way I write it is a bit dumb, but anyway, so this is just a vector space. So what you find here is actually, so this, you can write this as orthogonal direct sum of the kernel and the cohomology of the other side. So suppose I know quantum cohomology of X. Can I find quantum cohomology of X prime? And so I only have 2-3 minutes left. Let me very quickly say what I expect to have. In this generality, we haven't proved much, but so in some special cases, when this is not Fauré function, this is a Fauré space, as I said, link, and then in fact, just say local model. You observe the following phenomenon. So if you take quantum cohomology, as I said, this quantum cohomology of X, in this case, actually, so in the flap case, the quantum cohomology is analytic, but the radius convergence is only 1. But in this case, quantum cohomology is analytic in QL, and with radius convergence is actually infinity. So it's a global analytic function, but then you start to think about this QL as in P1, so as we did. So if you expand at 0, you get this. But what if you push to infinity? And when you push to infinity, what happened with this is so when you take in a neighborhood of QL equal to infinity, what happened with this is, so this is similar to what Concepcion explained, use this scaling equation. I didn't use scaling equation, I just used the Born connection. So sort of which would be similar, in fact, I think equivalent. Since in neighborhood infinity, this quantum cohomology will sort of decouple into quantum cohomology for X prime plus the this part, and then there is some kind of a irregular part. I'm sorry, so my time is up, so I will not be able to explain this too well. So if you push to infinity, and then there is a way to extract the closed system, which is regular at infinity, which will expect you actually get quantum homology x prime. And then there is some kind of regular part which will very much look like this, as I said, this R prime. And this irregular part will be, in this case, because of this, it will be semi-simple, but it will be looking a little bit like P R minus R prime in this case. But sorry, so my time's up. Thank you very much.
Any questions? Do you want to explain more about this?
Well, it's a little bit a long story. So anyway, so yeah. Anyway, so for example, if you look at the turbulent connection, and turbulent connection is regular, but when you energy continue to infinity, the turbulent connection in some direction become irregular. And so but you want, but of course all these are mixed. So you want to be able to extract the regular part out of this. And then there's some kind of classical theory of irregular connections or irregular D modules where you can decompose this into some way and solve differential equation. And so once you remove the irregular part, then you will actually get something which is equivalent to quantum homology of your flip. And so this part maybe it's worth mentioning that if you take, so as I mentioned, if in this case if R is equal to R prime, so sort of one limit, this will be flat and there will be no irregular part. But if R prime is equal to 0, that's exactly the blowout case, because it's a blowout of your S. So this will be your blowout of S. And so that will be, and so we're hoping to be able to get to. So now there's some kind of two way to approach blowout. One is to take some kind of limit of one discrete family of limit from flat to flip and then to blow up. Or you can just do it by the speculation I explained.
Oh, let's thank the speaker again.